Welcome to course number 2 of the Introduction to ROS. Today, you're going to create your own ROS package. And we're also going to show you how you work with Eclipse and IDE, how you import it and how you work with the IDE that helps you to program in C++. We're going to talk about the ROS C++ client library, which is the main tool when you interact with your ROS nodes and C++. And you're going to see how you create ROS subscribers and publishers, things that you've done so far through the console. Now we're going to implement them in C++. Then we're going to talk about the ROS parameter server and a RViz visualization tool. So ROS packages, as we already saw, are software in ROS. In the ROS environment is organized in so-called packages. These contain everything that a package needs, be it source file, header files, launch files, configuration files, kind of parameters. It can contain message definition, data, etc. Some packages depend on other packages. So if you have one package that implements an API with a certain message, it can depend on another package which defines this API. So when we say dependency is a list of packages that one package needs in order to be run and built. So when you create a new package with this command, cat can create package, you would type in the package name of your desired one and then give it a list of the dependencies. On the right-hand side, you see a typical structure of a package, where on top you would have a config folder if you have one, where you put the parameters, and we're going to talk about parameters later. And then you have, for a C++ package, you would have an include folder with then the package name for the C++ include headers. If you have launch files and you create some of those in the exercise, you would have a launch folder, a source folder for the source file of the C++ source files. And then, for example, if you have unit tests or ROS integration tests, you would put them in the test folder. There are two important files. The cmakelist.txt, which we'll look at in a second, defines the commands, how your package is built, and the package XML file. This one's kind of like a meta information file describing the name, the version number, the authors, and the dependencies of your package. And if you have package that creates messages, you would put them into the message or service folder, like here. We encourage to separate your implementation and normal package from the message definition, since the message definition should be as lightweight as possible because other packages might depend on. So if anything changes in your code, nothing has to change in this package. Hence, nothing has to change in the other dependencies. But you could put them in the same folder, but it's just a nice way in dealing with ROS, separating message definitions from source code. So first, I'd like to talk about this package XML file. This is a typical file actually from the template that you downloaded. On top, you would have the name, your ROS package template, and then some version number, a description, and then you'd have certain meta tags that you can specify. Very importantly, you would have to define here the build tool depend, which is the catkin that we use. And then you give it a list of dependencies. So in this case, it's ROS CPP, the ROS CPP client library that you need in this package, and the sensor messages in this example. For the CMake lists, we're not going to talk about too much how CMake works because it can be arbitrarily complex. There's more information on this website, but just to go a little bit through the steps that we often use. So on top, you will have the CMake version and then the package name. And then with find package, you would find other packages that your CMake needs, similar to the dependency in the package XML. And then in case if you had message definitions, you would specify them with add message files or add service files. You have to generate those with generate messages. And then you have to prepare your package for the export information, and that is done through the catkin package macro. And then if you have C++ code, you would add your libraries, add executables, and link them together. And then you would have special commands to add unit tests and installation rules. Now in the beginning, it's easiest if you look at existing CMake files. And here's one that we're going to give you for the next exercise. And I'm going to talk a little bit through the contents of this file. It's a simplified version of a extensive CMake list files. So on top, you have the project name again, and it's important that it's this exact same name as in the package XML. And then this means we're going to compile with C++11 configurations, which we use by default. And then here you list the packages of your dependencies, so the packages that your package depends on. And it has to be, these packages have to be also listed in the package XML. So in this case, we have the ROS CPP and sensor messages here defined as components. And then here we have this build, export build information. It has 4 points. The first one is the include directories, where you specify the directories where your header files, the C++ header files lie. Libraries are defined here. In this case, we don't have one. I just put this for completeness. And then Catkin depends is again the list of packages that if somebody depends on your package, he also needs as a dependency. So these dependencies lists are passed down from the lowest package to the upper one. So the upper package in the list, when it builds, has a complete list of its dependencies. And then with depends, you would specify system libraries. We don't have any here, but if in case you were to use Boost or Eigen, you would specify them here. Then you're going to tell CMake list how you want to build your project. And here you would specify, again, your C++ header include directory. So in this case, it's just called include. And then also you have to use this variable to pass it down all the other include files that are defined within the Catkin workspace. In this case, we build one executable, and this one you add here with add executable. We reuse here the project name, which is actually exactly the same name from up here as a variable. And then importantly, we add 2 CPP files. Essentially all the CPP files that we have in this project, in this example project. So one is the Husky high-level controller node CPP, and the class here defined at Husky high-level controller CPP. And lastly, you're going to need to link your library or your executable with the existing libraries, and you do this through the command target link libraries. So once you've built a project, you want to import it, for example, to Eclipse. And we set up already in your installation this command which builds the Eclipse project files. In the project file, there's a bunch of settings that these are automatically set paths and settings which are important for Eclipse to know how to use your code. So I graded out here, if you would have not used our virtual machine, you would have to use these commands to achieve the same. But since you're using our virtual machine, it's already pre-configured in a Catkin config environment. So you can only simply type Catkin build and then the package name, and this is already done automatically for you. The project files after you build are generated into the Catkin workspace in the build folder. You can start Eclipse. In the beginning, you'll see that you have to specify a workspace. You just press OK. And then you can import your project. So you go to File, Import, General, and then you say, it's an existing project I want to import. Then you're going to browse through that folder, Catkin workspace / build, and then choose the project that you want to import. Once your project is imported into Eclipse, you will have to tell it to scan your code such that you can use autocomplete, such that it understands the structure of your code. You can achieve that by clicking on, right-click on the project and then say index rebuild. And then you see it starts scanning your code. Once it's finished, it's nice because then you can nicely click. For example, if you click on a method name, it gets you to the header file, to the declaration or implementation. Same with variables. You can essentially kind of like browse through your code very easily and understand the structure. Important command is control space, especially in the beginning if you're not familiar so much with ROS syntax. With control space, you can use autocomplete, and Eclipse will just suggest, based on the current letters, what commands you might have meant. You can also build from Eclipse with Control B, and you would have to open up the console tab in Eclipse to build within Eclipse. It's nice since if you have an error, you can click on the error and it gets you right back to where you did where he thinks you did the error in your code. But of course, you can also build from your console, as you already know. You'll find once you click on the project, you'll find your source code within this folder source directory. And here are some other useful Eclipse shortcuts that you can use and get used to, such that you can be very quick with programming. So one is already I mentioned is the control space. If you want to comment or uncomment lines of code, you just do Control/. And we already pre-installed kind of like a auto format, like formatting guidelines, how you should format your code. And you can apply it by either selecting the entire file or portions of the code that you'd like to format and click Control-Shift-F to apply this C++ style guide. To move lines up and down, you can use Alt, arrow up and down, and to delete the line, it's convenient just to use Control-D. So once you work with Eclipse, make sure to go through this list again and practice a little bit these shortcuts to be a quick programmer. Okay, now I want to talk about the ROS C++ client library, or simply the ROS CPP package. Here's a very simple example of how a C++ program that works with ROS looks like. In this case, it's just one file, a main file, and it includes the general headers ros/ros.h. In the main file, it starts with ROS init to initialize, and this one has to be called at the very beginning. And in this case, it tells it the node name is called hello world. Then it creates a node handle, and we're going to talk about the node handle in a second. It's essentially the access point to all the communication that runs in ROS. In this case, it creates a ROS rate class and tells it, I want to run a rate with 10 hertz for this example. And then it goes into a while loop while checking ROS OK. ROS OK is always true as long as your node is supposed to be running. So in case some line of code calls ROS shutdown, or you as a user press Control-C from the console, this will be false, and hence your code will quit. So in this case, while the ROS node is supposed to run, ROS OK is true, and this while loop continues. Then it uses this macro ROS info to spit out the message into your console and to the log system. We're going to talk about this also in a second. And then it said spin once. Spinning means going through the list, internal message and service calls, etc., that ROS needs to do to enable the communication. So this is done via callbacks, and we'll see that also when we talk about subscribers and publishers. Spin once means just go through the current list that you have and work through it. And then in the end, your loop rate, the ones we define on top, would sleep 0.1 seconds, and then increases the counter, so it increases the number at 10 hertz and puts in your console hello world with the number. Quickly to the node handle, which is your access point to all the communication with other nodes. There are four main types of node handles that you can define. The default one is the public one, if you simply do ROS node handle and open and close the parentheses. And there's a private one, which we actually recommend if you work with nodes, which is marked with this tilde within the node handle in the constructor. There's namespace node handles. For example, if you do here node handles in ETH, means this is under the namespace of ETH. And there's a global one, which we do not recommend to use, is if you type in simply the slash. So if we had a node called node in a namespace called namespace, looking up for a topic called topic, then these would resolve to the following. The first one, since it's the public one, would be in, since the node lives in the namespace, we just look at namespace/topic. Now for the private one, all the private ones lie within /node. So it would be namespace / the node name and then /topic. If you use the namespace one, it would add another namespace to the namespace, so it would be namespace ETH topic. And the very last one is the global one, which is go to /topic. And the reason why we do not recommend this is because if you have multiple robots, suddenly you want to take all the nodes that are running into a namespace to separate, such that you don't have clash with the topics, etc. So if you use the global one, it will be very hard to find those and then have multiple robots on the same system. So stick to the default one or the private one. Then to the logging, this ROS info that we saw in the code. The ROS logging is a mechanism for you to spit out human readable text to either the console, to a log file, and then even publish it on this ROS out topic. So instead of using the classical stdc out command, we encourage you to use these macros that are defined in ROS. So in this example, ROS info. Like I said, this will automatically either put to the console, to log file, and also publishes on the ROS out topic, such that other tools can analyze the output messages of your node. There are different severity levels, such as if you have debug information or info, warnings, errors, and fatal, they would be differently colored, and you can sort with tools depending on the severity level. Here's an example, a table where you'd see, so the debug and info would be printed out on your console with the standard std out command, and warnings, errors, and fatals would be printed in yellow and red in your console. And for each severity level, they would also go into the log file and are published on the ROS out topic. These macros support the printf and the streaming style formatting. So in this example, you would have ROS info and then result, and you would here define a double. And the result here, the variable would have to be a double, and then it would print the result is this number. The same if you're more used to this stream style, you could do ROS info stream and then use these symbols to construct the output of your message. And it's nice if you look at the documentation, for which we provide the link on the bottom right. It has features such as conditional printing, throttled. If you don't want to fill up your console, you can throttle at a certain or print at a certain rate. You can delay, etc. So this is nice tools for you to print messages, human readable messages into the console and to the log file. Importantly, if you don't see the message in your console, you probably forgot to put in the launch file here the output to screen. This has to be set for you in order for you to see the messages in the console. Okay, so this is important. If you don't see ROS info, check your launch file and make sure that the output argument is set to screen and not to log. Okay, now I want to talk about the ROS CPP subscriber. You already know what a subscriber is. It's something that listens to a topic, right? In this case, I want to implement it in C++ and get this information from the messages. On the right-hand side, you see the listener node. It's the one example we already worked with in the previous lecture. So you have your main method function, and then it creates again a node handle, and then it creates a subscriber with this command. You can create a subscriber, it's called ROS, under the namespace ROS, subscriber, and then the node handle helps you to construct it. You would do node handle.subscribe, then the topic name, in this case it's chatter, the queue size, which means how many of the messages is it allowed to internally buffer. So the number can be arbitrary, but we recommend it to be between, I guess, 1 and 10. And then the callback function. So if it receives a message, what should I do with it? In this case, we tell it to go to the chatter callback function, which is defined up here. The chatter callback function is called whenever a new message arrives. And it gets as an argument the contents of that message. So in this case, it's a standard message string, and then it's stored in this variable MSG message. And what we do here for the example is simply do ROS info and say, I heard, and then the content of this message. So whatever you send on this topic will be printed out on the console. Importantly, you have to hold on to your subscriber variable down here. If you destroy it, it will not be able to listen to this anymore and call the callback. Okay. And in the end, like I said, we call this spin function. Previously, we called spin once, which once goes through this callback method. And if we call spin, it means just block here, don't continue, and just do the work that you have to do in order to receive messages and work with ROS services. So it waits until you quit the program. It makes sure the subscriber is continuously listening and calling the callback function whenever a new message arrives. Here is how we implement the publisher. So in this case, again, we have a node handle, and then very similarly to the subscriber, we create a publisher. And again, we use the node handle to advertise a topic. In this case, it's templated over the type of the string. With node handle dot advertise, templated over the message type. Then we define on which topic we want to publish. And again, we define a queue size. So in this case, it's over the type message string on the topic chatter with a queue size of 1. And we want to publish this message now at a loop rate of 10 Hertz. So we define here again the loop rate. And similarly to before, we publish it here. So this works by creating the message. Here, SED messages string, and then we call the variable message. Then we have to fill in the contents. Would be here message.data, and then we fill in the string that we want, in this case, hello world, and the counter as a string. We print it out in the console, and importantly down here, we call the publisher dot publish, and we give it the message variable. We call spin once to make sure it's published, and then again we sleep, increase the counter, and continue this process. Now these were very simple examples where we have one file defined as your node. What we encourage you to do is to program in an object-oriented way. In this case, our main file is very simple. It would initialize ROS, would create a node handle, and then create an instance of your class here called myPackage, and pass it, for example, the node handle if it needs it. And then you would have header files and CPP files, as you know it from C++ programming, defining your class. And typically would have one main class providing all the interfaces to ROS, being publishing, reading parameters, etc. And then you could put all the the things that actually do the work in separate classes and build up a nice object-oriented structure of your node. Here, what we encourage you to do, and you go as far as you want in this exercise, but typically what we encourage is to split the algorithmic part from the ROS implementation. So this part, the algorithmic part, could be completely ROS independent, could be used in other projects, and this package could wrap around your algorithmic classes and provide the ROS interfaces. Importantly now, you saw how we define callback methods. If you have classes, you want to have a callback on a method of the class. The syntax is very similar. You would define the topic and the queue size, but instead of just giving it the function name, you would tell it on this class, I want this method. And you would use here the ampersand to mark a function pointer. And you would tell it this to tell it it's from this class instance, okay? So whenever you want to have a callback on a method of your class, make sure to check out this syntax. Now I want to introduce you to the parameter server. It's essentially a global instance that stores parameters during runtime of your system. It's a very convenient tool since multiple nodes can access that data. And it's best used for configuration parameters, such as how many cameras do I have, which motor has which ID, etc. Things that don't change during the runtime of your robot. Here's an example of a parameter file which are stored in so-called YAML files. It's the format. In this case, we would have under the camera, we would define, okay, we have a left and a right camera with two names and give it an exposure number, for example. And then this is just a file that you can put down somewhere in your system. And then you have to load it. In this case, we can load it through the launch file. Here we have, as we know it, we load a node called name from the package and node type. And then we call this ROS param command, tell it to load. And then we're going to find this package. In this case, since we don't want to use absolute path, again, I can use this find package command. And then I put it under the folder config in a config.yaml parameter file. Importantly, you see now, last time we would have here self-closing tags. Now I want to load this parameter file under the namespace of my node. Hence, I have to put this ROS param command within the tag of the node. So I have here this simple symbol and then close down the tag here. You can also work with ROS parameters through the console. It's a convenient tool to debug. And if you do ROS param list, it gets you all the parameters that are stored on the current parameter server. You can retrieve parameters by ROS param get and then the parameter name. You would spit out the contents. And you can also set parameters to the console by saying ROS param set, the parameter name, and then the value you want to set that parameter to. Here I'm going to tell you how you can read ROS parameters within C++. So to retrieve a parameter, you would use the node handle again, and then tell it get parameter, get param, the parameter name, and you would have to predefine a variable in which it loads the value of that parameter. The method will return true or false depending if it has found the parameter or not. So it's a convenient way to check to make sure that you have actually found the parameter, found the contents. Again, similar to what we saw with the node handle, parameters can live in different namespaces. So if you use this in the beginning with a slash, that would call the global parameter name. In case you want to use the one defined in the namespace of your node, the relative to your node, just do not define here a slash and we get you the relative path of the parameter relative to your node. And for parameters, if we use this ampersand, we can use the private node handle. So all the parameters that are stored on a server are clearly marked. These belong to this node. On the right-hand side, you see an example where we use the private node handle. And then we want to load a string. Let's say we want to load a topic name. So we create this topic string and then call node handle get parameter topic and load it into the topic. What we did here is have it conditionally checked if returns true. If it's found, everything is okay. But if not, we spit out the message saying ROS error, could not find the parameter. So the user is warned he didn't define the parameter correctly and your program will not work as expected. Now, lastly, I want to talk about RViz. RViz is a very convenient visualization tool that you can use in ROS. It works by subscribing, similar to when you're using console to Echo, it subscribes to messages with a series of plugins. Then it takes the content and visualizes them in 3D. There's different views in RViz. So here's a 3D view. You can do top-down, side view, etc. And there's interactive tools to also publish. For example, if you click somewhere to publish this position, if you want your robot to drive somewhere. And importantly, once you've set up your RViz, you can load and save these configurations according to your needs. So on the left-hand side, you would have a list of display plugins, which you can add. On top, you would have a toolbar with tools, and on the right-hand side, there's the different view options, how you want to see the view of your environment. And on the bottom, there's some information about the time that is currently running. You can run rvis with rosrun rvis under the package rvis as a node rvis. If you want to add a new visualization, you would, on the bottom left, you would click this add button, and then you would have a dialog with a list of plugins available. So you see many things that you can add, for example, camera image, laser scans, maps, point clouds, etc. And for example, if I choose point cloud 2, then it would add it to this list. Now, one very important thing that you have to remember is when you want to visualize something, you have to visualize it in a certain reference frame. On top here in the global options, you have to define a reference frame that actually exists. Typically, it loads up, I think, with the map default, but if you don't have the map, nothing will show up. So make sure in the beginning, if you want to visualize something, to set this, for example, in the exercise to odom for the odometry frame, and a frame that actually exists in the system. And we're going to talk about frames in a later lecture, but for now, remember to set it here to something that exists. And then if I added this point cloud tool, you can open up with the triangle the settings. Make sure you subscribe here on the topic to the right topic that actually exists. And then you can go through, if you don't see anything, make sure that you have the right size, the right color, etc., and adapt this plugin, the visualization, to your needs. This is the end of lecture 2. What we're going to see in a second, we already talked about these links. I encourage you, if you start creating your own packages, to use the ROS package template, where if you find yourself, how do I do this? There's a very simple package which already compiles. You already have it on your system to check it out if you have questions first. And then again, if you have questions to how do I organize my package, lots of the contents of what we talk here is written down more extensively in this ROS best practices on our GitHub account.
All right, so the goal of today's exercise session is that you can really create your first own ROS package. And this package should subscribe to the laser scan of Husky. Husky has the possibility to add multiple sensors like an IMU or a laser scanner. And your package should subscribe to the laser scanner. Now, there's a hard way that you can do this, and there's an easy way. So if you think that you're capable of doing this all by yourself, then you can choose the hard way, which means that you essentially have to do the whole package by yourself. So you see here, point 1 is the optional part, which is a little bit more difficult. It says that package should be called Husky high-level controller, and there's a catkin command called catkin create package, which is going to set you up the entire file structure where you can put your source and your header files. And it also will create a CMake list and a package XML for you with the dependencies that you add. So this is really the hard way, because you have to set up the entire structure, the entire package by yourself. Then, since this might be a little bit too much for today, we also provide you an easy way. There's a zip file on the home page. That if you open this up, there's already the Husky high-level controller and already some files that are prepared for you. For example, there's a package XML, a CMake list, the source folder, and the include folder. So you don't have to do that. What you should do then is extract this You can extract this into your Catkin workspace, and I already have my implementation here, so I'm not going to do that. If you open up the package XML, it normally opens up your browser because it already has that stupid default application. You can go and change that to, let's say, gedit. And now you see here that it has two dependencies. It depends on the ROS CPP and on sensor messages. It needs sensor messages because there is the definition of the laser scan message, right? So I've already prepared this for you. There's the name ASCII high level controller, and yeah, that's pretty much it. There's as you make lists, that's also already finished, so you don't have to touch that, but look through it, try to understand it, such that if you once then need to do it yourself, you can take a look here and try to adapt it. Here's again the same. There's a ROS CPP and sensor messages defined. And also there are catkin packages, so if another package depends on this package, then the other package knows that it has the dependency of the sensor messages. So if you build a package on top of this, you don't have to specify the sensor messages again, but it then knows through this tree of dependencies that it also has to take in the sensor messages. There's, as I mentioned before, there's an include directory where your header files are stored. This is included here together with all the catkin include directories, right? And we then add here an executable, which is, if you go to the source folder, there's, as Peter has shown, we try to implement this in an object-oriented way. So there's a high-level controller node plus a library aside that. Now let me open up Eclipse so that I can show you the code. We really encourage you that you use the ROS package template. So a lot of the stuff that you need to write is already shown there. You just take a look and try to adapt what's written to what you actually have to do, right? So this is a really good guide, and it will help you out a lot and also teach you what the practices are, how you should do it, how does the syntax look like, stuff like that. And now you can import, oh, let me first build it. So it was pretty quick because I already built it. And you see here that there are additional CMake arguments with the Geclipse and the Unix make files, which are now going to create a package or a project description for Eclipse. Without this flag, you could not import it properly into Eclipse. So I can go into Eclipse, import existing projects into your workspace, next, and then browse to the build folder of your Catkin workspace. Okay, and now it shows you here all the projects that are, or all the packages that have been built in your workspace. And now you can, let me just select the ASCII high level controller here, finish, and now it is added to the Catkin workspace, to Eclipse. And important here is that, as Peter also mentioned, is that you right click on the project, go to index, rebuild. Because now if I, yes, something also important to mention is that if you open up the project, then there are all of these folders, and you should only change files that are in the directory source directory. So this subproject targets all of these files that they are automatically generated by the build process, and you don't need, or you should not touch these. So go into the source directory, then this structure is the exact same as you have in your source folder here. Right. Okay. So as I mentioned, there are two source files. One is the node, and the other one is the library or the class implementation. And if I now open up here the node, this is already provided for you in the zip file that you can download. And there are some tricks that you can do with Eclipse. For example, if you start typing Husky, you can press Control-Shift, and then it will show you a list of auto-completion. So I could, for example, choose here the namespace, Husky high-level controller, and then start writing Husky, Control-Shift, and it will automatically complete it for me. So really use these tools. They're extremely handy. Another thing is, if you hover above this, then it will show you a quick preview of what is actually the definition of this variable. And I can also jump by pressing F3, I can jump into this. Yeah. So, and then it directly jumps into the definition into the header file where this class is actually defined. Then another handy shortcut is that you can press no, okay. Now for the place where you need to implement your stuff is that if you now open up the zip file, then you'll see that in this Husky high-level controller CPP, it's completely empty. So there's only a constructor and a destructor. And you can now write all the code that you need to write to complete the exercise into this file here, and also into the header of this source file. Okay. So the tasks are that you first have to create a subscriber to the scan topic. So I quickly launch the implemented nodes, and ROS topic list shows me now all the topics that are around, and you can see here that there's a scan topic. This is the laser scan. So you need to write a subscriber in this class that subscribes to the scan topic. Then Peter has also told you about these ROS parameters, and we always encourage you that you use for a subscriber, since this has a queue size and a topic name, use parameters for these two things, because then you can actually change the topic name without recompiling, or in a launch file you can just specify this. So I'll quickly here show the ROS params that are around on the server, and it will show you here. So these are the two that I've created. So there are now not global, but they have here Husky high level controller and then scan subscriber queue size and scan subscriber topic name. Ross param get Husky high level controller, and then by pressing tab twice it will show you what it can, or what's actually around it. Then I can input here scan subscriber queue size, and I set the queue size to 1. You can also show the topic name, which is scan. Okay. So the end goal is that you have here, this is where I started the launch file, that there's an output of the minimum distance reading of the laser scan. So the laser scan is 2-dimensional. You just have one ray that goes like that of about, I think, 240 degrees. So you have a scan like this, just one. And I can show now this in, oh, let me first show you Gazebo. So this is the empty world now. And you could also use the RoboCup world that you've added before. Let me put here a box in front of Husky and now switch to Arvis. And then you can see here the laser scan of the box. So now, the way I did this, let me quickly delete some things. You can press here on add, go either by display type or by topic. So by display type means that you can add whatever you can add or Ross knows about. By topic means this is a list that only shows the stuff that's currently being published. So you can go by topic and then scroll down to scan, laser scan, okay, and then it will add here the laser scan. There are some options that you can change, like the size of the dots. So a laser scan is a collection of single points. You can increase here, let's say, the size of this, and then it is a little bit better visible for you. An important note is here in global options, the fixed frame is now set to Autumn. This is really important. If I would set it here to map, which does not exist, then it doesn't show anything in Arvis. And also, all the topics that cannot be shown show an error, meaning that there is no transformation between map and Autumn. So back to Autumn again, and everything is okay.